Yaskawa.
Good morning, everyone. Welcome to Yaskawa's Motion webinar, eCafe. My name is Kevin Hull, and today we're going to do a little bit different webinar. We're going to do an in-depth look at the functions in the PLC Open toolbox. So joining me today is Nishant Unikrishnan, Doug Meyer, and Mark Wilder, and together we're going to take turns doing some hands-on demonstrations of the function blocks live. So this will be a little exciting to make sure everything goes well for us. We're not going to do too much presentation this time with PowerPoint. And to start things off, we've got our boilerplate requests to keep yourselves muted, although I think these days we actually mute the entire conference line ourselves on this end. And as always, if you have any questions, please put them in the chat window. We'll try to address those as soon as we see them. Or if they're not pertaining to the topic at hand, we'll cover those at the end of the webinar. So these are the three main discussion points for today regarding the PLC Open Toolbox. We're going to walk you through the installation of these toolboxes. That has been a little tricky for some. And also we're going to talk about the documentation we've created for the function blocks. And then the majority of the webinar will be dedicated to, as I said before, the demonstration of the function blocks. And as a side note, there's some good news on both the installation and documentation for the toolboxes. By the end of the year, we plan to have a toolbox installer available, which will install all the toolboxes in an extracted format on your hard drive to alleviate some of the steps required today to make these usable. And that toolbox installer will also take advantage of a new feature we have in MotionWorksIEC version 2.3, which will allow the right-clicking for the help file to open from the toolbox function blocks. So I'm going to, right now, go to this quick link to yaskawa.com/IECTB, which is a quick link directly to the toolbox main page. And this page contains all the information for all the toolboxes for the MotionWorksIEC product line. So as you can see, there's a link to download the manuals, latest manuals, and also for each of the toolboxes we've published, you can download either the Express or Pro version if they're available. And since today we're talking about the PLC Open Toolbox, I'm going to download this current version right here to my PC. I'm just going to put this in my toolbox folder. Now there is a caveat here. This text instruction that was coming with this PLC Open Toolbox explains that you will also need the math toolbox in this case. And this is kind of a, right at this point, a legacy issue that we decided to create this math toolbox to allow us to have full compatibility no matter what the hardware line was. So whether it was MP2300 or MP2600, the same toolbox functions would work identically in both controllers. So we're going to also need the math toolbox when using the PLC Open Toolbox. And I'll just go back to the main page and download that as well. Okay. Over in MotionWorksIEC, I will then open that download. And extract it. I know I'm going a little quickly here, but I think most of you are familiar with this part of the MotionWorksIEC package. And as well, you can see that the PLC Open Toolbox contained the math toolbox inside of it. So I'm going to say yes. Okay, I should be ready to go. I should be able to use this toolbox now. So I'm going to do File, New Project, and make an MP2300 SIEC project. And the first thing I want to do is insert a user library. And I'll go find my new library from the toolbox directory. And the first thing I would demonstrate then is to add one of the function blocks from that library. And one of the most popular ones is access control. And you're going to see that we're going to have some typical problems come up. So if I just try to compile this, I get a lot of errors. And that would be expected based on the sequence of operations I just did. There's a lot of duplicate names, basically, of data types. And that is because the toolbox itself contains a copy of two of these data type files that are also available in a new project template. The toolbox needs those data types because it contains many of the PLC Open function blocks, and so it kind of serves as a basis for the PLC Open firmware library itself. So anytime you're using the PLC Open toolbox, one of the first things you have to do is delete the motion block types from your main project, and also the PLC task info types, because we already have a copy of these definitions. And if I hit compile once more, we're down to simply one error, which I do expect because I haven't included the math toolbox, as I was mentioning earlier. So I'm going to go back and add that one as well. The reason we need this math toolbox is because many of these functions are inside of them referring to functions from the math toolbox. So it's kind of a hierarchy scheme that the toolboxes use. So another little trick to remember here is I did extract it as part of the extraction of the PLC Open toolbox. And by default, MotionWorksIEC extracts libraries to its default libraries location. In my case, it's down here under the All Users Shared Documents, MotionWorksIEC 2 Pro, the Libraries folder. And that was Math Toolbox version 201. So I'll just pick that one. And try to compile again. I do expect one more error though, because I have not hooked up the access ref to this function block. Right, so we have eliminated all the errors due to duplicate data types. We eliminated the error due to not having the math toolbox, which these function blocks rely on. And if I were to define the access ref variable for this function block, we would have 0 compile errors and be ready to go. So that was kind of a quick explanation of getting the toolboxes down from the website and able to use within your project. And just want to say again that we're working to make this process a little bit easier. By the end of the year, we're going to have a toolbox installer that will download the extracted versions of all the toolboxes to save several of those steps. All right, at this point, I'm going to move on to talk about the first function block within the PLC Open toolbox. It will be the access control function block. I think it's the most popular function because it serves to enable the servo. It detects alarms, and it can also clear alarms. So it's basically just taking 3 of the PLC Open function blocks, MC power, MC read access error, and MC reset, combined into one. So at the very least, it's saving some code space in your project and also some debugging of additional ladder to kind of incorporate all those features. And there you have it. One function block can handle those 3 things. And so I'm kind of demonstrating some of the other surrounding interlock logic that's useful for enabling the servo. So I've got some one-shots here that will enable or disable when I change the enable request. And then my logic will keep the access enabled as long as the power is on. This is a global status bit. And as long as the hardware base block is not on, that's the safety circuit, the CN8 on the SGDV. And a couple other things I'll talk about with other function blocks I'm describing later on. But as you can see, I have a 2-axis demo kit system, and my axis 1 has a warning currently. And the warning, this is part of the feature of the axis control function block, is we break out the difference between whether it's a controller side alarm or a drive side alarm. And so it becomes clear if you look at these output values in hex, which is the same display format on the front of the amplifier, that right now I have an A91 warning, which is displayed right here under the drive warning ID. And this was caused by actually clamping the motor so it could not rotate just a moment ago. I can clear that warning by doing the alarm clear input. And now that's cleared out. You can also see the status. This is a direct copy of the status output from MC Power. And that's basically what the access control function block does. It's a 3-in-1 block, basically, that allows you to enable and clear alarms in one. At this point, I'm going to switch discussion over to Mark Wilder, and he's going to explain a couple more blocks in the toolbox.
Thank you, Kevin. I'm going to talk about a couple of very simple toolboxes that are going to make your life a little bit easier. The first I'm going to talk about is jog. Now, of course, PLC Open has the capability to do jogging. It's just not a very intuitive method of doing it. It uses the MC move velocity function block to actually cause the jog. However, as with all PLC Open function blocks, it's the rising edge of the execute that causes that motion, and removing the execute bit does nothing to stop the motion. So you need to use a separate function block, MC stop, in order to stop the motion. Additionally, anytime you make changes to the inputs of the function block, the velocity, the acceleration, the deceleration, you need to reassign the execute, give the execute again so that the next rising edge will cause those changes. We've done all that logic for you and put it into a single function block called the jog function block. With the jog function block, and we'll see it in operation in just a second, we have two separate inputs, one to command forward motion, one to command reverse motion. As long as those inputs are high, it will continue to do the motion. Once you remove the forward input, for example, then it will stop the forward jog. Additionally, we have logic in there so that if the velocity, acceleration, or deceleration change, those changes are made on the next cycle of the scan. Let's take a look at that in action. Here we have the jog function block at the top. When I give it a jog forward command, you can see that we jog right up to that velocity of that we have assigned, right now 10 units per second. I can go ahead and change that velocity. If I change that to 15 units per second, you can see down here that our velocity has now increased with no new rising edge of the input block, anything like that. It changes automatically. Also, if I remove the forward jog command, we go to a stop at the acceleration rate which we have assigned. This makes it very easy. It saves you from putting in multiple jog blocks. Normally you would have to do separate jog block for forward and a separate jog block for reverse, or switch the direction bit. And there's a lot of logic involved in that. This jog block makes that a very simple task. The outputs of the jog function block are a busy input. If we are executing a jog move, the jog busy will come on. Once we are at the velocity that we're commanding it to go, we will see the jog in velocity come on as well. And once we exit the block, for one cycle, the done bit will come on. Now we can't actually see that in our operation, so I put a count up timer here so that every time I execute a jog command, we can see that increments by 1. So that is coming on for 1 bit. We also have the error codes as well. These are the same error codes that the MC jog velocity uses. Another function block that we have to make things simple is the position limits function block. Let me go back to my presentation. Position limits are actually built into the drive. There's a couple parameters that actually control the position limits in the drive. And when you first power it up, it's going to use that hardware configuration as your software position limits. Using PLC Open standard function blocks, we would have to use read parameters and write parameters in order to change those on the fly. Now, of course, you may not need to change them on the fly. If you need fixed limits, then you can just go ahead and set those in the drive parameters, and that will be no problem whatsoever. However, if you do need to change those during the operation, then this position limits is going to make it a much easier task for you. So again, using standard PLC Open function blocks, we would have to use parameter read, parameter write function blocks to change these parameters. And we've eliminated that need. And in addition, given it the ability to enable and disable on the fly as well. So you can have software limits sometimes and turn them off and not have them active for other times. Let's again take a look at how this works actually in IEC. Here's our second function block. You can see right here is the position limits. Just for our visual purposes here, I have the read actual position down at the bottom, and I'll just go ahead and set that to 0 for now. I have a positive limit of 100 units, a negative limit of -10 right now. If I just go ahead and start a jog, we'll see that this position is actually going to go past 100. And the reason for that is because at this point, even though the function block itself is enabled, the limit functionality is not enabled. That's the limit position enable input. So if I now enable that, my motor comes to a stop. I get an access alarm because my position has exceeded the positive position limit. So let me go ahead and reset that. So now I'm going to go ahead and leave that limit position enabled, and I'm going to now give it a command to move in the negative direction. And that did not work. There we go. So even though our limit position is enabled, and our position is greater than our positive position limit, because we're actually commanding it to move in the negative direction, it's going to allow that. And once it gets down to its negative position limit of -10, you'll see it comes to a stop. And it comes to a stop using the maximum deceleration that the drive can provide. So again, that gives us this access alarm. And if we go ahead and reset that, we'll move back in the forward direction. And it's all pretty straightforward from there. So again, when we hit the limit, it's going to come to a stop as soon as it hits that limit once we have that function enabled. An additional feature of this particular function block is that it also provides an echo of these limits to make sure that those were set correctly in the drive. And I think that's all I have for this particular function block.
Or speed or decel value.
Right. And you can see that here in this jog function block as I showed earlier. Right now, Our jog velocity is 15. You can see our actual velocity down here is also 15. If I go ahead and change our jog velocity with an overwrite here, you can see our actual velocity goes up to that same amount. If we were to do that using standard PLC open function blocks, then we would have to trigger the execute. It needs another rising edge in order to change that speed. All right, I'm going to pass the mic over to Nishant Unnikrishnan, who's going to talk about a few more function blocks.
The two function blocks I'm going to talk about today are move relative by time and read access parameters. Both these function blocks are available in the PLC Open toolbox. The first function block is move relative by time, and as the name implies, this is a relative motion function block. It should not be confused at any point with any absolute motion. This basically is used for commanding a relative motion from the point where the axis is currently. As you can see, there are two main inputs into this function block, the first one being distance. And the distance input basically uses the value that is given to it as a relative move or a relative distance that needs to be moved from where the axis is currently. The second input is time, and it uses the time, splits up time into three intervals, the first one for acceleration, the second one for constant velocity, and the third one for deceleration. So the time that is given is split into three to create a trapezoidal velocity profile for the axis. And as you can see here, the area under that trapezoidal profile will be the distance that that axis moves. And like I mentioned earlier, this contains an MC move relative inside this function block. This is the calculation that goes inside the MC or inside move relative by time. The total time that's given as an input to the function block is broken into an acceleration, T1, constant velocity, T2, and deceleration time, T3. The distance is used to calculate the velocity, and using velocity, we calculate acceleration and deceleration inside the function block. Features of this function block are that it can be aborted at any time by another motion function block, and also if the user puts in a time less than or equal to 0, an error ID specific to this function block comes up. Looking at implementation here, this is an example where the move relative by time is being used to index an axis. Index distance is 360 units, and the 360 units are being commanded over 1 second. One interesting or important feature of this function block is that it's built based on PLC Open specifications of inputs and outputs. So as you can see here, the outputs of this function block are excuse me, clearly in line with the PLC Open, with other PLC Open function blocks. So you can see these are familiar PLC Open outputs: the done, busy, active, command aborted, error, and error ID. And while the axis is in motion, the busy and the active bits are on. And once the axis is completed its motion, the done bit comes on. And in this case, it comes on only for one scan, so it'll be difficult for us to visually verify that. I can change the time, real time, because in the code, in the interlocking code, I am firing the move relative execute after one of the moves is done, and there's a little bit of dwell time in there. So I can change it to 2 seconds, and you can see that the busy and the move and the active bits will be on for 2 seconds. So it's basically taking 2 seconds now for completing its move and then indexing after a small dwell. A quick view of the logic analyzer plot shows the start and stop of this block. Expand it a little bit to show how the trapezoidal profile gets generated. This is the execute bit where the move relative by time function block got fired, and this is the done bit where the move was done. In my code, I have a little bit of dwell, half a second dwell, and then my next execute gets fired. You can also see the velocity profile, the trapezoidal velocity profile, where you have acceleration for 1/3 of the time given, constant velocity for another third, and deceleration for the last third. So this is useful in applications where time-based moves need to be commanded, and it's a pretty simple block to implement. It's got just distance and time, and it is fired using an execute block, or I'm sorry, an execute input. The next function block we're going to look at today is read axis parameters. The read axis parameters is a collection of about 60 MC read parameters and MC read bool parameters. And these function blocks are basically the PLC open function blocks that are used to read parameters that are relevant to axes that can be read from the controller. Now, the read axis parameter basically contains all, like I said, 60 different MC read parameters and MC read bool parameters, and it helps the user to read all relevant axis parameters using one single function block here. So you can read it all in one place simultaneously. The various inputs to the read axis parameters. The first one is a familiar one. It's an axis ref, so it decides which axis parameter needs to be accessed. The second input is a structure, and it's of the data type of that particular variable is axis parameter struct, and it is defined in the data types file of the PLC open toolbox. That's a structure that contains all different parameters that need to be read for that axis. The third input is axis type, and this is used to define what kind of axis we're trying to read parameters from. The different axes that are supported are servos, variable frequency drives, steppers, virtual axes, and external encoders. Now, we made this an input into this function block to optimize the performance of read axis parameters. Like I mentioned earlier, this contains multiple, up to 60 MC read parameters. So it may not be optimal to read all parameters for all different types of axes at all times. For example, some parameters like commanded position or commanded velocity, commanded torque, or commanded acceleration may not be relevant for external encoders because these parameters cannot be commanded for an external encoder. An external encoder can have only feedback. And so if, for example, the axis that we're trying to read or access is an external encoder, then the code internal to this read axis parameter function block blocks it from reading commanded position or commanded acceleration, because these commanded values are not available and would have given us an error if we tried to read commanded position or commanded velocity from an external encoder. So, so this function block basically prevents a user from wrongly trying to read parameters that are not available for a particular axis. And so it helps you. It basically prevents a user from making mistakes or getting errors on trying to read parameters that are not available. The last input to this function block is param types. And currently we have 3 different types of parameters that we read. The 3 types of parameters are basic parameters, status parameters, and cam parameters. Again, this input is for optimizing the read process for read axis parameters. For axes that are not synchronized or not being used in the synchronization process, like camming or gearing, you do not have to read any cam parameters because they do not have cam parameters. For example, if there is even for camming applications, the master axis in question does not have CAM parameters. All the CAM parameters are relevant only for slave axes. So depending on the type of axis and the type of configuration we have for a particular axis, we can choose to read or skip reading a few of the parameters. And again, this param types input is a input that can be used to mask certain read functions. Let us look at an example where we are using this function block. Here's an example where I have a demo program which has 3 axes connected to it, configured on it. The first one is a servo axis, which is also a CAM master. And you can see that that servo axis has axis type 0 as an input. It has also, and since this is a CAM master, I am not reading CAM parameters for this particular axis, so I'm basically masking that particular bit in that word by typing in 4, and 4 corresponds to 100 in bitland, and it basically is masking my CAM parameter read. Since this is a CAM master, I do not have to read my CAM parameters for that particular axis. My second read axis parameters is for a virtual axis, which is a slave, a CAM slave, and the axis type for a virtual axis is 3. And I'm reading all parameters, basic, status, and CAM parameters. Since this is a CAM slave, it does have CAM parameters relevant to it. The third axis I'm reading is for an external encoder, and I'm blocking out everything except my basic parameters for this axis, for my external encoder axis. Let us take a look at how these parameters show up on our on the watch window. This is the list of all servo parameters that I am trying to read, and you can see here it contains all basic and status parameters, actual position, and since I am commanding position for my CAM master, this is basically the commanded position. And you can see here that this is a linear axis that basically keeps going in one direction. And the parameters that are being read using this function block are listed in the help manual for the software for all axes. They're listed as axis parameters, and they're in the help manual for the function blocks. And this is a comprehensive list of all the parameters that can be read for a particular axis. For my virtual axis, which is a slave or CAM slave, you can see here that it has all the relevant position parameters and all command. It probably does not have. Since this is a CAM axis, it does have all the CAM parameters too that are getting updated every scan that this is being read, since it's enabled throughout. And lastly, we have the external encoder, and you can see for an external encoder, since I'm reading only the basic parameters, only a few parameters are getting updated here. It is important to note that if all parameters need not be read at all times, you should place, or you should never, remember never to place this read axis parameter block in a very high priority, fast task, because internal to this block, it is really reading all parameters at all times. So it is important to pick and choose or wisely decide which task this particular block should go into. Now, if there is a task that requires very high-speed updates of commanded position or actual position, one should use an MC read bool parameter or MC read parameter in a fast task just to read that particular parameter, and not put this read axis parameter into that block or into that POU, which is getting updated fast, because that can be that can affect the time that it takes for that particular POU to get processed.
All right, good morning. My name is Doug Meyer. I'm a senior project engineer here at Yaskawa. And this morning I'm going to talk about 3 additional blocks. And some of these are, I guess, a larger combination of some of the ones we've already spoken about. So let's get started with the product buffer. The product buffer is actually one of the more popular blocks, actually. I was talking to Kevin about this yesterday, and we probably have close to 150 to 200 machines installed in the field using this particular block. And what it does is it stores captured or latched positions from an axis and keeps them into a circular buffer for use elsewhere in the program. And very useful for those continuously running type applications that require registration or synchronization, things like labeling, cut to length, maybe a thermoforming type axis, where some sort of process needs to happen to capture data, but you might have additional latches come in before you can finish the process. So you need somewhere to store them temporarily. So the main features of this product buffer is it has a place to store the captured data up to 100, but it is a configurable size, as we'll see. It has a built-in latch function using an MC touch probe. It also has, for those applications or maybe machine modes where you just want to do some testing, or you don't want to use the actual latch input of the sensor, you can set if you activate that test mode input, then you can just give it triggers from the program. And it also features the 3 main pointers into the buffer that we're going to talk about next. That is the store pointer, a use pointer, and a previous use pointer. Now, this block has this input called registration data. And registration data is of a certain data type called a product buffer struct. So let's take a moment to look at the product buffer struct for just a second. The structure contains 12 elements. 4 of them are for configuration. That's for the buffer size, the sensor that is going to be doing the latching, a manual offset, and then a lockout distance to help prevent false triggers and false data from being stored in here. There's the 2 main elements for storage of the latched positions or captured positions. One is the cyclic buffer, which if you have a rotary axis that's modulating on a machine cycle, it would always give you the latch position within that machine cycle. And whether you have the axis configured as a rotary or linear, you always have available to you the non-cyclical position that starts from 0 and pretty much goes forever. And then the other 6 are for usage of the function block itself, the main ones being the pointers. For those that have used this block or attempted to teach other people how to use the block, it's also helpful to know which are inputs to the block and which are outputs. And we'll see there's only a couple of key outputs, that is the latched positions themselves and the storage pointer location. Inputs to the block that the user needs to provide are to specify the buffer size and the sensor, the manual offset, and the lockout distance. And then the program is also required to update the use pointers and the previous use pointers. The other ones that have a gray box are there, but they're for use elsewhere in the program. There's nothing inside the product buffer block that does anything with those 3 for sensor distance, sensor offset, and product away distance. So having said that, so now we know what the structure is a little bit, let's take a look at the buffer layout itself. And first of all, the buffer size. So this is the length of elements in the buffer. So the pointers will increment starting from 0 up to this buffer size -1. The storage pointer is the next available location to capture, and the function block will automatically increment this pointer when a new value is loaded. And if the storage pointer ever catches up to the previous use pointer, then it will signify sort of a wraparound type condition where the elements have not been consumed as fast as they've been put in, and so that will generate an error for the block. The use pointer and the previous use pointer, the only thing that the block does with these is initialize them to 0, or set them to their initial values rather. The use pointer will be at at the front of the buffer. The previous use will be put at the end of the buffer. But the user is responsible for incrementing these, and typically the program will identify some sort of difference between the store pointer location and the use pointer location, and that will trigger that current value to be used. So let me give you an example of how the buffer flows. So initially, the use pointer and storage pointer are set to element 0. Previous use is always one behind, so it's set to the top of the buffer. And say we get a latch, a captured position. So the storage pointer puts it in element 0 and then indexes itself to the next location. The program then detects that difference, and it'll trigger that value at index 0 to be used. Now, the beauty of the buffer is that while that process is going on, we can capture another value as shown here. So here another value came in, the storage pointer incremented itself again. Now the process is finished and the use pointers are incremented. But it's noticed that since there's still a difference between the use pointer and the store pointer, another process has started, and then the values will be incremented again until once again the use pointer and store pointer are equal, and the process will simply just wait for the next captured value. One of the only tricky things about the structure itself that sometimes causes some confusion is the sensor input, because it's a data type trigger ref, and it's really a pointer to which input on the axis is going to be used for the latch trigger. So there's more help in the toolbox help file, but here's what it is. So for our demo kit, we actually have an LIO-01 card installed, and you have two options. If you set the bit to 0, it'll use the C channel of the encoder. We recommend, and in most cases, I would say all the cases in the field, we just use the high-speed input on the encoder card, and so that's actually fixed at digital input number 1. The other values that are in that structure, things like a lockout distance, is the distance that it must travel after it's first been captured before the latch will rearm itself. And if we have some sort of match point, the sensor distance is the distance upstream that the sensor is from that match point. And then we have a couple of offsets available for use. So I'm going to give you an example here of how to use the product buffer. Simple box diverter, say we capture a box upstream, 24 inches upstream, and then 24 inches downstream, it's just going to kick it off to the side. So you can use the box sizes and spacing and pitch, things like that, to help determine what are the settings for your buffer size and your lockout distance. So in this case, you do have to configure a couple of the inputs for the product buffer. So here we've configured our buffer size, set it at 6. We've told it which sensor input to use. We've set the sensor distance and a lockout distance. And I've just left my offsets at 0. So let's show you how this works here. We'll enable the buffer right here like this. And as an aside, this is a simple way to do a little toggle bit here by using a rising trigger and a little set reset function. And this yellow thing here is what's known as a toggle boolean. So if we define this input in our worksheet as a toggle boolean input, then I can check this toggle boolean values, and it's very helpful for remote debug. Okay, so the product buffer is enabled, and I've placed this into a watch window so you can see the values change. So the previous use pointer is set at the top of the buffer, and the storage and use pointers are set to 0. So now I'll come down here, and now before I do this, I'm going to run the master here. So I go back, and you can see that, again, our applications tend to build on itself. So we always try to use the toolbox functions whenever possible. So I have an axis control block here for each of my axes. I'm also using the read parameters block that Nishant just described. So I'll enable my axes. I can run the master. and now I'll capture some inputs. I'm working with a special demo kit that we have where we have some signals looped back. So some of the outputs and the position of our main axis 1 is fed back into the external encoder. So if I trigger some latches to happen, we see that my storage pointer just incremented. Here it is again. And if I look at the buffer, you can see that every time I get a latch, it'll store it into the next location. And when it reaches the top, it'll wrap around. So the product buffer does the first half of your application. The second half is actually using those buffered values, and it always requires some sort of customized function block to use it. So here I have my little detection where I detect the difference between the use pointer and the store pointer, and then I run this calculation. And inside here, we take in the buffer data at my use pointer location, the non-cyclical value, use things like the sensor distance and the manual offset to create a new target position, and then I update the pointers, just like this. So here's my customized calculation, setting a new target position, and then making moves. I'll show you a little screenshot of a trace. Here's the latch input coming in. This first value here is our store pointer, and then the use pointer. And then here's my little axis 2 moving out and moving back to kick the box out of the way 24 inches downstream. So this latch input here causes that motion, this one causes this motion, this one causes this motion. All right, we'll move on to the home LS pulse block. And it's a fairly straightforward procedure here. Provides a complete homing routine. It'll move an axis to a limit switch and then reverse direction and find the motor C channel, and then move to an offset value and establish a new position. So this is used, a typical application is just about everything. Even applications that use an absolute encoder need some sort of reference routine. It could be something like this that you might have in your program. So before using this function block, be sure to first enable your end of travel limit sensors. And then second, it's highly recommended you set parameter 1.1 equal to 1. It will default to 0, which means that when you hit an end of travel limit, the axis will disable itself in that direction. That's not really desirable for this type of application, so if you plan to use limits, we recommend that you set it to 1, which is to decelerate the motor to a stop and set a servo lock condition. Basically, that means just keep it enabled. So you'll find that inside here, it's really a combination of PLC open functions in a sequence. First, it uses a MC step limit switch to go find the limit. And the deceleration, as you'll see from the trace that I show you, is essentially immediate, but it can be torque limited if you need by setting a value in parameter 406. Then it'll move on to an MC step ref pulse, which is searching for the C channel. That's the creep part of this function. And the creep for this function block is always performed opposite direction of the approach or the search for the limit switch. Then it does a MC move relative, and then finally it sets the position for your new absolute position. So you can see that here. If I switch to this example, just by opening the function block and scrolling through here, here's our step limit switch, move relative, step ref pulse, another move relative, and then a final set position. So this is a great example again of a handy function that saves the user from having to reconstruct all of that code every single time. A little more about this home structure. Inside the home struct, which is also placed inside the axis structure, by the way. You have things for setup, which is direction and switch mode. You have your approach configuration, your creep configuration, and then your offset and new position configuration. There's also a bit in here for homed. This is all user controlled, so the function block does nothing with this. This is for external use. Typically on a power-up that requires homing, you would initialize this to false, and then at the end of the procedure, the user program would set it to true and things of that nature. There's also two tricky ones in here. The direction is an enumerated data type of a data type MC direction, and only the positive direction or negative direction are valid. So that's an integer of 0 or 2. And the switch mode, which is kind of determining how it should respond to the limit switch, and only edge on is supported. So it's really the rising edge of the switch is the only thing that will activate this. And you also notice that there are some limits for the approach and the creep. You have a distance limit, which is the maximum allowable distance it can travel before it aborts out of the function, or a time limit. And they can be active simultaneously. Either one of them can be deactivated by setting their value to 0. So, so let's take a look at this. Now, I wrote this note here for myself to remind myself that before you run this, because it has a search for the C channel, it uses a latch function. Okay, so you got to make sure there's no other MC touch probe functions active, like the product buffer. So I'm going to have to go back here and be sure that I shut off my master here, and then also stop the product buffer. So the rest of the homing setups can be set anywhere. They can be set in the program. I've chosen to set them here in my initialize code. So just for axis 1, .home is where all the homing elements are placed within the axis structure. And you just go through and set these. This axis is actually a 0 to 360 degree rotary axis. So I just set my XL to 50 revs a second, approach at 10 revs a second, and so on. And at the end, I'm going to set a position of 0. So let's just simply trigger this. So while it's searching, you'll see that it is busy, and then done came on for one scan. And if we go to the logic analyzer, we'll take a look and see what happened. So here's where it started searching. This value here, the cyan value, is our commanded velocity, so it's searching in the negative direction. And here it's running negative. And then it found our end of travel limit, and it did a little bit of a backup move just to get off that limit. So it reversed direction. So this move is a positive move. Then it started creeping in the positive direction until it found the C channel, at which point it went back to the C channel. So if you notice here, you can see just a little bit of a negative velocity. That's because it does actually stop, back up, and return to the position of the C channel. And then it makes its final offset move forward and sets position to 0. Now you see this little dip here in the position. That is because when you search for the C channel, the end of it does actually set a position automatically. So it set a position to 0, and because it's a rotary axis, it rolled to between 0 and 360. So it actually did roll a little bit. But since this offset move is a relative move, it doesn't matter. And what matters is when it gets to the end, it defines the position that we want, which is 0. And the last one that I'm going to talk about is the high-speed output. So we've used this in a couple of high-speed applications, and what it does is it provides a method for activating an output at high speed independent of the task scan interval. So some of the applications that might need this are some sort of converting or labeling, maybe a printing, or to trigger a vision camera to take an inspection. Something where on-the-fly external events have to be triggered based on axis position. And so this is a hardware thing. So the output is associated with an external encoder channel. So to use this, you need to use one of these available products, basically an I/O card that has an external encoder input. And that includes our single-axis controller. And then the high-speed output is a fixed output. Most of these, it's digital output 1, except for the LIO-06 card, where it is digital output number 7. To turn the output on, the output will turn on within 13 microseconds of reaching the on position value that's been set. And this on position value may be changed on the fly. To turn it off, it'll turn off after traveling either the minimum distance that's set or the minimum time that is set here at one of these two inputs. And the actual off is not high speed. Okay, so the actual off is dependent upon the application task rate of where you've placed this function block. So I'll show you this application right here. So here's our high-speed output block, and the way we've set this one up is, again, we have another jog block, so I'll run this master. I'm just going to run it at a higher speed, though, so it's going at basically 10 revs a second. And since my high-speed output was enabled, you see it is starting to turn on this output every about 10 times a second. And right now, it's turning it on at a position of 90 degrees as I go around from 0 to 360. If I hold this on, it'll change it to turn it on at 270 degrees. So I can change my position on the fly. So if we trace that, I'll show you what the trace looks like. Here's my high-speed output that's toggling. So if the toggle input is on, my target is 270 degrees. So here's the external input going from 0 to 360, and it's about 270 degrees. The scope actually shows 272, so it's a little misleading because the scope is tied to a task rate, so the data may not reflect what's truly happening. We would have to put it on an external scope to really verify that it happens at 13 microseconds, but trust me, it does. And then the same with the off time. It's set at, I think, what I put in here, 20 milliseconds. So that varies a little bit with the task rate. And then you see when the toggle input goes off, it immediately changes to a target of 90. So since this was already past 90, it waits until the next time where it crosses 90 and turns on again. So now my target is at 90 degrees. Okay. So that's those three function blocks: the product buffer, a home limit switch pulse, and then high-speed output. And with that, I'll turn it back to Kevin.
Just want to point out again that in every case here, these function blocks we're talking about just compound or add what's already existing in the product via the PLC Open firmware library. And in this case, with the high-speed output, there's about 4 parameters that are corresponding to the high-speed output on those cards you mentioned. And you could write this code yourself, but we've wrapped it up for you and automatically refired function blocks to write new positions when appropriate, and really saves probably at least a couple hours in each case if you have a situation where you do need that functionality. Okay, we're just about finished. I was going to speak about 2 more function blocks in the PLC Open toolbox before we conclude here. And so to show you my next function, which is called axes interlock, right now I'm gearing 2 axes together at a 1-to-1. And this will help me demonstrate the axes interlock function block, because that function was designed for applications where, let's say it's a gantry that has X and X prime, so 2 servos running the same mechanical system. And it'll work for either a linear or rotary application. So in the case of a gantry, that's basically set for linear mode typically, where the axes are captivated on slides, maybe run by a ball screw. But we've had a number of other applications that would be rotary mode as well, that have 2 motors that share the same load. And so this function block will work for those applications as well. And what it will do for you is to monitor that both axes are within a position tolerance that you specify, and that neither of them has any alarm, and give you the status as one Boolean output to tell you that everything is okay with those axes and you're okay to keep them running. So right now I am actually gearing, I am actually moving the master, and they are in motion. And let me show you the axes interlock monitor function block now. It's just sitting right here. I have to specify both of the axes involved with this mechanical setup, and I specify a tolerance that I want to make sure they stay within. So in my case, these are degrees, so that's a generous 3.5 degrees in my case. And if there was any actual position offset to account for, the math will handle that if you have some offset that is known. So right now, this output called locked is telling me that those two axes are within 3.5 degrees and neither of them has any alarm. So they are running. You can see the deviation kind of fluctuating here, about, well, maybe 1/3 of a degree, plus and minus, because they are in motion right now. And if something were to happen and jam one of these axes, or there was a fault, this output would immediately drop out. And then it's up to the user to decide how to take advantage of this monitor feature. And in my program, let's first see this. I'll jam one of the axes. So that didn't take much at all. I mean, as soon as I touched the master basically, I got more than 3.5 degrees of error between the two motors, and this output shut off. But what that did for me as well in my program is I use it as an interlock on the axis enable. And so my enable status dropped out for both axes, so they shut down. They do not continue to run if there is something wrong with the position of either axis, so you don't cause any mechanical damage. So that's basically what that block can do. It's a simple feature basically to be used as such. And finally, another function that we've developed, again, is kind of for adding to the integrity of a system. And this one is an absolute encoder position manager. And this one is a little more complicated to talk about. Its goal is to give an indication that the absolute encoder position is valid, as seen by this output here. So right now, I have been running this system. My absolute encoder position is valid. What's happening inside this block is there's an MC set position function block. There's a Y reset absolute encoder function block. And there's also a read axis alarm function block. So it's kind of taking those three features and combining them into one. And that's a key point to this block being of service, is that you would have to use this block and no other means of resetting the absolute encoder or setting it, because to do so outside of this block would defeat the purpose of its ability to detect and determine if the position is valid. So there's actually a retain output used in this case. So even after power cycle, this block can show that the position is valid, and it remains valid until there's any kind of encoder alarm related to the absolute encoder. So that's its key point of operation, is any time there's an encoder related alarm, it does a reset coil on its position valid output, and it will stay off until the alarm is cleared and until the set position input is executed. So let's demonstrate that real quick. I can actually demonstrate an encoder alarm by disconnecting the encoder from the amplifier momentarily. Okay, so at this point we don't have an absolute encoder alarm yet, but I have unplugged the encoder and reconnected it. You'll see that if I switch over to the axis control function block, there is an axis alarm, and that alarm is AC9, which means encoder disconnection. Okay, so this alarm is not clearable by simply a casual alarm clear, but it requires power cycle according to the documentation in the servo pack manual. Well, in addition to that, we can actually clear that via software by resetting Mechatrolink, because that causes a soft reboot of the servo packs. So if I reset the Mechatrolink, the AC9 alarm will disappear. It did disappear, and now that the amplifier has reset or restarted, we've lost our position valid output. And that is because now the amplifier is displaying an encoder-related alarm. So I have an axis alarm, it says A82, and that's what the amplifier is showing on its front panel right now. So I'm using this output again in some interlocks to enable the servo, or to actually move the servo in an automatic mode. So now we're prevented from doing that until we resolve the situation with the absolute encoder. So I need to first reset the absolute encoder, and that would remove the A82 alarm. It did do that. The alarm is gone. If I look back at the access control function block, the A82 alarm is gone. We do have a controller side alarm now. Okay, so all alarms are cleared on that axis. And at this point, I still do not have a valid position. And that is because I need to reset the position. I need to physically move the axis and calibrate it back to a known position and define that position and set it using this function block. And at that point, I now have, once again, a valid absolute encoder position. And so now my interlocks used elsewhere in the program are happy and would allow me to do any automatic modes of operation. Okay, so that was the last block we had to discuss today. I think I wanted to cover one more thing briefly once again. We talked about the forthcoming ability to download all the toolboxes, extracted format, with the help files coming by the end of this year. But as of the 2.3 release, which came out less than a month ago, the software itself now supports the ability to launch the help file by right-clicking on a toolbox function block. And I can do that. I can demonstrate that right now. If I right-clicked, I can see the Axis Interlock help file documentation. And the simple trick to make this work on your version of MotionWorksIEC 2.3 is described in the release notes. You simply have to download the CHM file from our website that we mentioned at the beginning of the webinar, from yaskow.com/IECTB, and put that CHM file in one of the directories of the user libraries folders and rename it a specific name. But that's described in the release notes for MotionWorksIEC 2.3. It's a relatively easy procedure, and once you do it once, it should be fine for all times that you use the toolbox. There was one question there at the end asking about the reset Mechatrolink in conjunction with an MP2600. And that is a limitation right now of the MP2600. The Y reset Mechatrolink function block does not work on that hardware platform because to reset the amplifier would actually cause a soft reboot of the option card or the MP2600 as well. So it's very different behavior than would be experienced on the MP2300 system with Y reset Mechatrolink. So we have plans to add another function block called Y reboot controller, which would be a more appropriate name for a function describing the behavior that one would have on the MP2600. And that would basically allow you to accomplish a very similar sequence as we just showed here to clear the amplifier alarms that need power cycle. With the additional caveat that the controller itself is also resetting. So there would be some slight difference in performance or in behavior there. Okay, at this point we want to conclude this webinar and thank the other panelists once again, Nishant Unikrishnan, Doug Meyer, Mark Wilder, and myself. My name is Kevin Hull. Thanks a lot, and we'll talk to you at the next webinar. Have a good day.